Return to generalized Hooke's law. So this thing is called generalized Hooke's law. And so, this is a tensor equation. Sigma ij is the stress tensor. Epsilon KL is the strain tensor. And C ij KL is the generalized elasticity tensor. Okay? And so how many components does C ij KL have?
81.
81 components, right? Because I, J, K, and L all go from 1 to 3. So 3 times 3 times 3 times 3 is 81, right? And this, when you get up to like third and fourth order tensors, you kind of really see the difference. We always treat second order tensors like it's a matrix, but what it really is like a vector of vectors, right? And so then, a fourth order tensor is like a vector of vector of vector of vectors, right? Yeah. And that's how the mapping works. Okay, so if it had 81 unique components, that means we'd have to go to populate it. We'd have to go to the lab and do 81 experiments, 81 different experiments, just to get the material properties for one material, right? Sounds kind of hard. Well, luckily, there's some things we can do to simplify it. We're talking about a Cauchy stress here. So the Cauchy stress, we already showed that if depending on how you say it, if angular momentum is conserved, then the Cauchy stress is is symmetric. Or if you impose symmetry on the Cauchy stress, then you automatically conserve angular momentum, right? So in our case, we're always going to work with symmetric Cauchy stress. And so if the Cauchy stress is symmetric, then that means that I and J can be transposed so that C I J K L must be equal to C J I K L. Likewise, the strain tensor is symmetric. So since the strain tensor is symmetric, C I J K L must be equal to C I J L K. And then I think in the other lecture on elasticity, I talked about that, C can be derived from a strain energy density functional. Okay, so when I say strain energy density functional, you can think of it just like, those of you more familiar with thermodynamics, like a Gibbs or Helmholtz free energy, right? So it's just some statement of the free energy that includes work that's done by deforming the material, right? So if you have some strain energy density functional, then C is defined as the partial, or the tensor gradient like this, and the order, like all differentiation, the order of differentiation can be reversed, right? So we could write it like this. Or we can write it like this, right? We can reverse or do the order of differentiation differently, and we'll get the same result, right? So because of that, we also have that C ij KL is equal to C KL ij, right? So that's called major symmetry. And the others are called minor symmetries. So with those major and minor symmetries, things reduce down to 21 components. And with 21 components, we can use a little bit different notation. So this is called Voigt notation. And what we're going to do is write our, instead of a tensor equation, we're going to reformulate it into a vector equation. So now we have a stress vector and a strain vector, and C is a matrix. So I'll write out for this kind of material with 21 components what that is. And this is where things get a little boring, but I'm just going to write it out once. Because the order does matter, so we're going to have the diagonal components first. Now note for the shear components, there's a 2 in front of the strain terms. And so anytime I write a matrix like this and I don't fill in the other side of the matrix, that's because it's symmetric. I'll try to write symmetric there, but if I don't, that's what it means. Okay. So this kind of material is called a triclinic material. Now, good thing is there's not many materials that are like that because we still have to go to the lab and do 21 experiments to populate that thing.